Yeah. So Emanuele Silvio Gentile will present his work about the importance of atmospheric ocean wave coupling in deterministic and ensemble regional kilometer scale forecast in mid-latitude cyclones. So just a few words about him. So he's from Italy. Where are you from exactly, by the way?
I'm originally from Bologna, and I've been in the UK in the last 6 years or so.
Okay. So he was, I mean, many people here were involved in the HIMEX program, so have also many links with the Italian community. So he moved to the UK first for a bachelor in physics at Imperial College London, and then to Reading, which is not that far away from London, for his PhD. So he's currently a third-year PhD candidate, and so expecting to finish his thesis in autumn, as I understand, this year.
Yeah, exactly. In December 2021.
Perfect. And so his work is about this the impact of atmospheric wave ocean coupling on extreme surface wind forecast. So that's what he works telling about today. So him and he has three supervisors, Gray and Janet Barlow, who are at Reading University. But I think I see you have 4 supervisors on your slide. So Hugh Lewis also from the Met Office, and John Edwards. I don't know him.
Yeah, John Edwards is just he's he's an expert of the boundary layer and its interaction with larger scale motion, and he's in the same team of Dr. Hugh Lewis, who is the manager of the scientific prediction team at the Met Office now.
Okay, perfect. Yeah. So you are somehow linking, so somewhere between the Reading University and the Met Office. So now I stop talking because people are here to listen to you and not to me. And so the floor is yours, and so you'll speak for about 45 minutes, more or less.
Yeah.
And then we'll have time for questions. So
thank you very much. All right. Thanks so much, Florian, for this very nice introduction. For me, it's a pleasure to be here today with you, though in a virtual format. And yeah, just share these results with you and hear your feedback and your ideas and questions about it. As Florian was saying, we are concerned with the importance of atmosphere-ocean wave coupling in a deterministic and ensemble regional kilometer scale forecasts in mid-latitude cyclones. And we're carrying out this work across Reading and the Met Office. I think Florian knows some of my supervisors. Maybe you also know them. And I think Florian kind of introduced them very well. And the models we've built and I will talk about today have been also developed with lots of other people that I'm not naming here in the talk, but doesn't mean they didn't contribute to the work. And they are from Met Office teams. So just to give you a bit of background to the research, and what really happens in the UK is that every year we get lots of wind. And to be a bit more specific, we have lots of extratropical cyclones that hit the UK every year. And they're associated with extreme surface wind speeds, which are characterized as exceeding the 90th percentile of the climatological distribution. And these wind speeds cause really quite a widespread damage to infrastructure, power network, and so on. And the damage is proportional to the cube of the wind speed. So even small forecast errors can lead to quite an important impact in the sort of correct estimation by insurance, for example, of the damage, or even prediction for first-line responders to act upon the forecast. So we really need to tackle the source of forecasted errors. And we know from work of Lawrence that traces back to 1969 that the weather is quite a chaotic system. So even small errors in the initial conditions and small errors in the model physics approximations of the atmospheric processes can grow exponentially over time, and they lead to quite a large uncertainty in the extratropical cyclone wind speeds. So we really need to generate the probabilistic realizations of extratropical cyclone events. And this is best done by using an ensemble prediction system, which I'm sure you quite know there in France. And you can sample and provide guess on the forecast uncertainty. I'm not sure how much you are in the British bundle, let's say, but I will just mention this. In 1987, Michael Fish, who was a BBC forecaster at the time, received a phone call from a radio amateur asking, was quite concerned, now is there a storm coming? And Michael Fish dismissed her, saying, well, if you're watching the forecast, there is a storm coming. And that actually turned out to be one of the worst storms of the last 2 centuries. And this is called as the Great Storm, known as the Great Storm in the UK. And so what really shows that back in 1987, we couldn't really forecast the weather correctly. And maybe ensembles are giving us an additional weapon, let's say, to get this right. But according to recent research, we might still have missed it. And this is because there are still so many systematic errors and our initial conditions are still, in a sense, poor, that there is lots of uncertainty in our system. And an important source of the model errors is the C-state independent parameterizations of their C-fluxes, which control, at convective scale, the extratropical cyclone wind speeds. So what we've really seen in recent years is that there has been quite an integration of the atmosphere, ocean, and wave models, which used to be quite common for the climate studies, but it used to be much rarer for numerical weather predictions. And these are very high fidelity modeling of RC interactions compared to atmosphere-only model that can really lead to coupling, reducing the systematic errors in the forecasts. And this coupling between different model components is showing potential for a much more accurate prediction of the severe weather events, such as, for example, the historical winter storm series that Whale et al. In 2017 looked at, finding a reduction of 8% and 3% in wave heights and wind speeds associated really with forecast scale improvements. And you might be familiar, much more than myself actually, with the work of George Varlas et al. From Hellenic Weather Center in Athens. And they looked at medicanes using coupled system and saw quite improvements. A very fascinating medicanes, although it's not really the topic of the talk today. And then going to my co-supervisor work back in 2019, they could really see, looking at months-long simulation studies, that there was an about 20% forecast scale improvement in wind speeds upon coupling to ocean, with the wave feedback being the most relevant. Now, if you look at the map here of the scattered green dots, you can see that for most sites, the coupling to waves, so coupling to ocean and waves, really improves the relative root mean square error for winds and waves. And this really shows that we're getting this figure much better with a much higher fidelity in coupled systems. So this kind of provides the motivation for our work today. And the questions we are really going to be concerned with concern first the deterministic approach. So we wonder whether coupling the atmosphere, wave, and ocean components in a numerical weather prediction can represent more closely the boundary characteristics and in turn improve the surface winds and gas forecasts that are associated with extratropical cycles. And second, we are going to ask ourselves, if there is a signal, which we will see there is upon coupling, is that impact important when we compare to other sorts of model uncertainties, such as initial condition, lateral boundary condition, errors in the extratropical cyclones extreme surface wind forecasts? So this is going to be addressed with 2 different case studies. The deterministic case study will concern extratropical cyclones Ali, Helen, and Brona that crossed the UK between the 16th and 20th September 2018. And the second case study, we have developed an ensemble coupled convection permitting system focused on the UK, and we'll explore it in the simulation of the extratropical cyclone Kira that crossed the UK on the 9th of February 2020. So let's start with the first then, the impact of coupling on deterministic forecasts. As we can see, the synoptic situation between the 17th and 20th September 2018 is quite interesting. We get a storm coming, let's say, quite off from France, southwestern direction, going northward and crossing the UK on the 18th. And then we get storm Ali, and then we get storm Brona on the 20th. Ali was the most intense storm of the 3. So looking a bit more in detail of the experimental setup that we really used. As I already said, the case study period is between the 16th and the 20th September 2018. and we use the UKC4 system developed by the Met Office, and this is C stays for coupling, and 4 is the fourth version that we've developed upon years. The initialization time was 1 day before the very first storm, just to allow for coupling spin up, and the model domain sees a 1.5 and 1.5 kilometer grid here focused on the UK, and then we increase it to 1.5 and 4 kilometer if we go outside a bit, we step to the edge. So it's a variable resolution domain, and that's why the operational domain is also called UKV, a variable resolution, V for variable resolution. So we set up 4 different configurations. The very first configuration, which we shall call A drag 1, is the atmosphere only with the UKV drag parameterization. So we're using the operational drag parameterization. Then we change the drag parameterization, and we use therefore Coare 4.0, which you might know, but we add a cap from Donnellan 2018 results, and then a decrease at high wind speeds. We will see a bit more in detail in a second. We then use an atmosphere ocean configuration, and that you can see here. I'm not sure if you can see my cursor, but yeah, this is coupling between atmosphere and ocean. So from the atmosphere, it sends the wind, pressure, temperature, radiation, and surface fluxes fields to the ocean, and it receives back a dynamical SST. And this is very important because the SST in the atmosphere component is persist throughout the simulation time, it's just fixed. So of course, a different SST is going to change the boundary layer stability and so on. When we also couple to atmosphere, ocean, and wave, then the atmosphere sends the wind component to the waves and receives back the wave height, period, and surface stress. And we also embed a coupling between the wave and ocean. So a fully coupled atmosphere ocean wave system. It's quite important here to see the node hours of the simulation. And as you can see, as we increase the coupling, let's say the complexity of the model, the node hours increase. And of course, this is something we should think of, because when you have, let's say, 17 ensemble members, not just a deterministic model, then of course the computational time increased more and more. So we want to then understand whether just changing the drag parameterization can bring some benefits with respect to a fully coupled system. So looking with a bit more detail of the drag parameterization in the drag 2 results, I mean, this is quite a well-known laboratory result from Donnellan in 2002. And we see here the linear dependence up until 33 meters per second, so moderate winds of the drag coefficient, and then a saturation above it. So we have 2 parameterization that we are actually modeling in the system. So the natural drag coefficient just increases with the 10 meter wind. But then in the drag 2, we have a much steeper increase, a bit closer to the sort of laboratory result, a cap at 27 meters per second, and then a plateau value from Xu et al. 2017 results. So what's really here the physical basis? Also, you might ask me very rightly about coupling. Of course, the main assumption here is that the Money-Obuchov similarity theory holds in the surface layer. Now, maybe some of you are familiar with the works from Sullivan in 2014 and 2008, where they show there is a deviation, especially in light wind condition, from the sort of Money-Obuchov profiles, but they hold quite well when there is some sort of wind wave equilibrium. So I think that we think that these are a reasonable assumption to start with, at least in a coupled model. So we start by looking at the gradients of the 3D velocity vector B, 3D scalar T, temperature and humidity, and we see they depend on the momentum flux T tau node, the sensible heat flux H node, and the moisture flux E node. And if we look a bit here at the picture over the ocean, what we can see is that as the wind starts blowing over the sea, the sea becomes rougher, and this increases the surface stress, and we have a downward transfer of momentum. At least this is the kind of feedback we would expect when we're modeling the situation. And also a dynamical SST will have an impact on sensible heat flux and heat flux. So we then can go forward and parameterize a bit, put some formalism, some machinery around these ideas, and we can start seeing that the wind speed follows the log dependence. Then we have a momentum, a roughness length that is parameterized as a function of the coefficient and the friction velocity U star, and also the viscosity for the light winds contribution. And of course, alpha is constant when we are concerned, for example, with A-1 or atmosphere ocean. So it's an empirical constant set to 0.011. And when we then couple to ocean and waves, and in particular to waves, the Charman coefficient is simulated by WaveWatch 3. And we then look at the momentum transfer coefficient and scalar transfer coefficient that are also parameterized as a function of the momentum roughness length and the height itself and the von Karman constant and so on. And it's quite important to know that over the sea, the latent heat flux dominates. So the scalar transfer coefficient for moisture is set as that for the heat flux. So we can then express the parameterization for momentum, heat, and moisture turbulent fluxes that will be then used by our surface layer scheme in the model. I mean, I think you know these equations already, but what's really important to note here is that the momentum turbulent flux in the case of strong winds conditions, depends just on the 10 meters square wind speed, because the surface currents are on the order of centimeter per second. So if you have a 20 meter per second wind, this doesn't really change much the overall wind shear. And we can also see that compared to a persist SST case where the surface temperature denote is fixed, a dynamic sea surface temperature T of T kind of gives us a change, of course, with time in the delta T. And this reflects into the heat flux. And because the buoyancy flux accounts for the moisture heat flux by the virtual potential temperature, we could have changes in the overlying boundary layer stability upon changing in sea surface temperatures. And I think there are quite interesting study. I think it's Dr. Joachim Vollmann, and he's now at the Karlsruhe Institute, and he looked at the sort of changes in dynamic SST and how this is affecting the fog forecast. So the very first, let's say, results we are looking at it today are the sort of biases that are inherent in the forecast of these extreme wind speeds, because we kind of want to have a first order understanding of what's going wrong in our atmospheric model, or if actually we should be happy with it. And what we can see is that looking at the comparison between in situ, these circles here, this in situ 10 meter winds value, gust and sea surface temperature, overlaid on the corresponding model variables for the day when Storm Ali is striking the UK, what we can see is that the 10 meter winds and gusts are overestimated by up to 5 meters per second in most of sites, with biases up to 10 meters per second. And also we have some quite large biases for the SST as well, with biases of up to 1 Kelvin. So I think this is quite an unsatisfactory representation of the atmospheric state by the atmosphere overlay with the operational UKV drag A-1. And it's important also to say that these biases are consistent with what Lewis already saw. So they fit in the bigger picture of 1 month long testing. So we then look at the sort of dynamical performance over the time of the 4 different configurations. And I mean, I think you all can see here a peak in the 3rd simulation day, on the 19th September 2018, the 4th simulation day between 72 and 26 hours. And we can see that there is, especially at the peak time, quite a reduction in the 90th percentile of the meter winds upon coupling to ocean and waves, and the change in the dark polarization, the green and red lines. But for gusts, all the lines are pretty much the same. I mean, very much overlapping. So there is quite a negligible impact on the 90th percentile of gusts. If we then look at the sea surface temperatures, we can see that the mean sea surface temperature in the atmosphere ocean wave is reduced by up to 0.5 Kelvin. So it goes from 288.2 to 287.7. I mean, something like that, 0.5, 0.6. And, this is sort of interesting because it's really telling us that the coupling to ocean here is responsible for most of the difference also in coupling to ocean and waves. So we're already starting to isolate some sort of the feedbacks, as coupling to waves being important for wind speeds and coupling to ocean for SSTs. So if we then look at the spatial distribution of the impacts, what we can see really is that there is no clear pattern in the 10-meter winds and gusts reductions or in enhancements in the atmospheric simulation compared to the sort of closest to operational model A-1. But there is a very consistent reductions by up to 2 Kelvin if we look at, okay, here's the cursor, up to 2 Kelvin if we look at the sort of distribution of the impacts. And this is because the ocean is stratified after surface heating through the air. So the oceanic mixing that is simulated by the NEMO model is implying a surface cooling. If we then look at the reductions upon coupling to ocean and waves, we can see that a much more consistent picture starts with Praco Valley and also for gusts, although less so, while the changes in SSTs are most likely linked to bathymetry. You know that there is quite a shallow area here called the Dogger Bank, which used to be a very big landmass that connected the EU to the UK, a sort of geographical Brexit, if you allow me the joke. There was a flooding of it, but the bathymetry is still quite shallow. And this might be linked to this ocean wave coupling, where we have enhanced turbulence via the momentum being transferred from waves to ocean with an upwelling of the warmer water in the Dogger Bank, which is being quite warmed up because it's shallow bathymetry. So we then decided to look at the boundary layer characteristics changes, picking up, for example, a point here in the North Sea, where, if you remember, just go back to the previous slide, there was quite an impact in the reduction of waves. And looking at the position of this point in the front, given by the equivalent potential temperature, we can see that this is within the cold front, as also highlighted by the boundary layer depth, which is quite high, goes up to 1.6 kilometers, something like that. So if we are in the cold front, and what you can see here is that if we look at the potential temperature profiles, there is a clear reduction in SST, of course, induced by coupling to ocean in the cold sector. And therefore, the profile of the potential temperature is far more stable than, well, not far, but it is more stable than the A-1. And so we can see this also from the boundary layer height, which is highlighted here as a sort of line with experimental error associated with it. And yeah, it is decreased from the 1,100 meters in the A-1 to 780 meters. If we look also at the wind shear, that's also increased in coupling to ocean and wave in the A-2 compared to atmosphere ocean and the sort of close to operational A-1. And so this leads to a far more turbulent boundary layer than AO and A-1, and we can see that the red boundary layer depth is enhanced, is increased compared to the blue, which is the AO, and also the green here is which is the A-2, the change in the drag parameterization boundary layer is increased compared to the A-1. So this increasing turbulence leads to enhanced turbulent eddies, which leads in turn to increase, as we expect, momentum flux. But is this something that is happening only for this point in the North Sea, or is something that is consistently happening across the domain? Let's have a look. So if we see the sea is covered by young growing waves over the 19th of September, this is the wave age map here. And corresponding to that, we have an increase in the Charnock coefficients, which is enhanced, of course, by coupling to waves up to threefold. We see the difference here of A with respect to A-1, so it's up to 0.002 larger, so 0.0031 compared to 0.0011. So then we see that associated with these enhancements, there are correlations with enhancement in aerodynamic thrust and also in momentum flux. So what's happening here is that the waves are giving rise to a force which is proportional to the wave-induced stress, which is increasing the frictional drag, which is in turn decreasing the surface wind speeds. These results are new in terms of the mechanism, because they were already observed by Janssen back in 1980, theorized by Janssen in 1989, then observed by Doyle for the Naval Research Laboratory, Whale, as I said, and George Varlas, and then you, of course. But if you then look at the change in the drum parameterization, we see a very, very similar picture. We see the decrease in the wind speed again corresponds to enhancement in momentum flux and enhancement in aerodynamic roughness. We can really see the same for gusts as we saw a bit for the AOW configurations already. And that's because the way the gusts are being modeled in the model, and there are sort of balancing effects. The reduction in intermittent winds is led by more friction at the surface, and so this is leading to enhanced gustiness. So this is only leading in the end to only a slight reduction in gust. But what's really interesting is that the momentum flux and the aerodynamic roughness, and therefore the surface stress by the parameterization I discussed at the beginning of the talk, are quite comparable in size to that induced by the young growing waves. So what we would be really interested to do now is investigate the drag coefficient distribution with 10-meter winds for 2 different points in the domain across the simulation days, and they are highlighted here and here. So let's have a look. So we see that the green, which is the change in the drag parameterization, and the red, which is the coupling to ocean wave, are much steeper than the blue and the black, which is the AO and the drag 1. And we can even see that A drag 2 is even more steeper than AOW, drag coefficient dependence. And this is much explaining the fact that we see more reductions in the 10-meter wind speeds upon the change in the drag parameterization than just coupling to ocean and waves. But what's really interesting here is that also the plateau here that we are seeing a bit with AOW is also kind of modeled by the A drag. So what we're really seeing here, that the change in the drag parameterization is quite capable of mimicking the physics of atmosphere-ocean wave coupling for the range of the simulated wind speeds. We then look at the sort of impact the different configurations have on the forecast bias. And we see, we do this by looking at the percentage difference in the 10-meter wind root mean square error statistic. Again, as you'd expect from what I've already said, so nothing new. There is no important improvement in atmospheric ocean compared to the, let's say, closest operational atmosphere model. But there is an up to 20% improvement, at least over the North Sea, upon coupling to ocean and waves. So the wave feedback here is quite clear and is bringing down the forecast bias for these 5 days. And this is where also Ali is striking. So this is really better physics for the simulated high wind speed conditions. Over land, the picture is slightly different as we don't really have a clear improvement, and for some sites there is even a degradation of coupling to ocean waves. But then, if we look at the comparison of the change in drag parameterization to the fully coupled atmosphere-ocean wave, we see that there is no clear forecast scale improvements obtained. And that's really interesting, because what's saying here is that overall, on average, across the observations sites, change in drag parameterization is achieving the same forecast bias improvement as atmosphere-ocean wave. And this is achieved, very interestingly, by the change in drag parameterization, by saving the 20% of the atmosphere-ocean wave computational cost. So we are getting most of the physics of a fully coupled configuration by just changing the drag parameterization. Of course, these results really apply to the high wind speed physics. We would need to test the drag parameterization also for, let's say, lighter wind speeds in order to draw more conclusive assertions. So in order to, let's say, you've seen the impacts of coupling to ocean and waves, and you might wonder, as I did as well almost 1 year ago now, what's the actual importance of these improvements in coupling when there are other sources of model uncertainty in the extropical cyclone forecasts? For example, how does this compare against the initial condition errors or lateral boundary condition errors? Is the signal of coupling robust enough for the ensemble simulations? The case study we looked at is the Storm Kira case study. The Storm Kira originated from a fairly weak area of low pressure in the southeastern US on the 5th of February 2020 and intensified while traveling across the North Atlantic. And also at 9 UTC on the 9th February 2020, we saw the maximum intensity of Storm Kira, and the mean sea level pressure was located just here north of Scotland. And we see here the structure of the strong winds with the 95th percentile highlighted by the cyan lines, and up 28 meters per second. And this is just at a meter wind speed, so you can just imagine the value of the gusts and the damage this caused. This was the most intense storm since 2013 to strike the UK. The frontal structure was quite messy, although the cloud band was quite clear from the 700 hectopascal relative humidity. But we used the boundary layer depth to look at the fronts, and that's quite nice, actually, as we can see the boundary layer quite high here. So, it's a cold sector, and then, warm sector here with much smaller, lower boundary layer depth. Okay, so how did we really set up this coupled ensemble system to look at this case study? We started by downscaling the 17 Mogreb's G ensemble member initial condition and lateral boundary condition perturbations to a 2.2 kilometer grid. And we added those to the UKD analysis, which is, you probably remember the operational model I mentioned. This is just analysis of the metosis very high resolution analysis. And we obtained perturbed initial conditions and lateral boundary conditions, which initialized 17 different MET-UM forecasts. So we're here in the flow chart. If you can see my cursor, I hope so. And then, according to the sort of experiment and configurations we wanted to achieve, we could switch on or off the stochastic physics RPG scheme for just one parameter or all parameters of the physics parameterizations. And to set up the coupled forecast, we then use the UKC4 dynamical core, and that's the deterministic ocean model and deterministic wave model. I mean, these are just named for just ocean model, IMM15, Atlantic margin model, and SMC for the wave model. All right, so let's have a look a bit closer look to the configurations. So we started with an atmosphere only configuration, and this atmospheric configuration only has initial condition perturbations, with the global Ostia and the sea surface temperature boundary condition persist. And this is again very important because it just means we have a static sea surface temperature field across the simulations. Then we decided to switch on the perturbation to the Charnock parameter up to CRK ends. Again, sorry for the naming, is a bit challenging. And then we switched on the full stochastic perturbation scheme, and this is what we call the control ensemble configuration because it's the closest to the operational configuration. And then we have an atmosphere ocean coupled and atmosphere ocean wave coupled, and this is the very same as the control, but just with atmosphere ocean coupling and atmosphere ocean wave coupling. I would just like to highlight that in the atmosphere ocean wave configuration, there are no stochastic perturbations from the Charnock because the Charnock is provided by the wave model, and this is very important. So the very first experiment looked at isolating the different feedbacks from stochastic and initial condition perturbations. And we can see, as we expect from other results from Metoffice people, that stochastic perturbation, which are represented in full by the black boxes, really enhance the ensemble spread of Kira 95th percentile wind speeds. But the stochastic physics we can see consistently shifts by up to 0.5 meters per second, the mean and the median. I mean, not shown actually, by the median of the atmosphere only. And then when we have also the stochastic perturbations to Charnock parameter alone, then we have the same impact as when it is applied to all the model parameterizations. At least this is what it seems from this plot. But if we look a bit closer to the timeline of the upper whisker, which are these upper whiskers, upper and lower whiskers, especially for the lower whiskers, we kind of fail to capture some of the stochastic sensitivity in the Kira intensification hours. And this is a very key point because the Charnock parameter stochastic perturbations are fixed. So there might be the fact that we don't have a time sort of dynamic simulation here. So other feedbacks become more relevant than perturbations to Charnock. Just looking briefly at where the spread of the control configuration as standard deviation ensemble members with respect to mean, ensemble mean, is located. As you probably would expect, actually, it's located at the borders of the high wind speed region, where this gradient that goes past from 8 to 10 meters per second. And it has a very good spatial agreement with mean sea level pressure spread. And each ensemble member is really forecasting slightly different tracks and frontal positions for Kira. So initial condition perturbations provide each ensemble member with a very different synoptic scale forcing. And so this spread is quite likely linked to the initial condition perturbations, which dominate over the contribution from stochastic physics, because we see the spread is very small here for the features. So we then are ready to look finally at the impact of coupling to ocean and wave. And I guess the very first striking feature of this graph is that the red and the black, which is atmosphere, ocean, and control, are very similar. Like there is really almost an overlapping, which really shows that coupling to ocean impact is quite negligible, at least for this sort of general score. But when we then look at the green, which is the atmosphere, ocean, wave coupled, we see a consistent shift in the ensemble median and mean, again not shown, of 1 meter per second because of coupling to waves. And this is confirmed by the hourly plot of the upper and lower whisker spread, but the lower whisker is less reduced. So overall, the spread of the whisker in the AOW is a bit compared to that angle. So if we expect more impact on the ocean system, see that actions are fairly localized, for example, of Ireland, but they relate quite well of Brittany with SST reduction in temperature. You probably know this already from the previous slides I was discussing, that the boundary layer is quasi-neutral in the high wind speed regions. So, for example, of Ireland, and there the turbulent kinetic energy budget is dominated by the wind shear. So the enhancements in stability in the boundary layer away from the high wind speed regions that are labeled here by the black dashed lines, and that's where actually the change in SST is having the largest impact, because we're away from the regions where turbulent kinetic energy production by wind shear is dominating. So actually changes in stability is important. If we look at the map of the spread in SST, we see that both in AO and control, that's increasing poleward. So that's quite striking, the fact that coupling to ocean is not really changing the spread across simulations, and this really reinforces the idea of introducing perturbations directly from the ensemble system of the ocean. Very, very interesting here. We look at the ensemble mean of the 10-meter winds, and we see reductions of upon 1 point by up to 1.5 meter per second for most high wind speed features, and that's compared to the control ensemble system. So very consistent uniform reductions by coupling to waves, and it's quite neat the fact that we are seeing these very much confirming the deterministic results from before. And we have again a very good spatial agreement with the distribution of the Charnock, and we see again a very much increased here, actually twofold of the Charnock parameter, not threefold, and this might be because the ensemble is moving out the sort of deterministic signal, because we're anyway simulating with different initial conditions. So we are actually less so increasing Charnock than in deterministic, but it's still quite striking because it's twice the control value of the stochastic perturbed Charnocks. What I'd really like to highlight here as well for the Charnock parameter is the time variation, the time evolution actually of the Charnock distribution. We see that for the upper quartile, the spread of the Charnock is actually growing with winds, peaking at peak wind time and then slightly decreasing. So it's really following the sort of behavior of the winds. But again, the largest spread that we see is for the lower values, and that's because those lower values are located here at the frontal boundary. So that's really again linked to initial condition error. So we see again the fact that we don't have a perturbation in the wave model, they are just really linked to initial condition perturbation in the atmosphere, is somewhat not producing the largest perturbations where we would like them to be. And overall, the feedbacks here, you probably, again, it comes from the deterministic sort of explanation. The growing young waves extract momentum from the winter flow. I think, again, what's really nice to see in the ensemble is that this is consistent for the ensemble mean. And if we then look at the wind strike probabilities, which is basically the probability of the ensemble members of exceeding the windstorm threshold, we see that, as we expect from previous results, that coupling to ocean wind strike probability are nearly identical to the control ensemble. So these are not really, the impacts from coupling to ocean are not really retained if we look, let's say, over the whole day. But the impact from coupling to waves, so when we switch on also coupling to waves in the couple to ocean configuration, we see a massive reduction in size and extent of the high wind speed features. And you can see this even more from the differences between the control in A and C, panel A and panel C. So difference between panel A and panel C. And this, of course, validates the consistency of the dynamical interpretation that was suggested by the instantaneous different maps. So we can really combine all these different plots and really see that the impact of coupling to waves in the high wind speed conditions, very important caveat, is very robust. So in conclusion, today we started with quite annoying positive biases for winds and gusts and SSTs in exotropical cyclone weather conditions, which were an unsatisfactory representation of the atmospheric state. And we then saw that coupling to ocean and waves could lead us to some interesting feedbacks within the deterministic system. So, for example, reductions of drag and enhanced air momentum flux, seen both for boundary layer profiles and also for spatial distributions. And we could also see that just a change in the drag parameterization could capture atmosphere ocean wave physics, saving the 20% of the computational cost. And we could also see that this change in parameterization and atmosphere ocean wave coupling were yielding about the same improvements in the forecast bias. We're looking at the root mean square error with respect to in situ observations. And we then looked how robust the impact was in the ensemble system. And we could see that the coupling to waves yielded robust reductions and consistent reduction on both ensemble mean and median. And this, I think, motivates further studies from us on the topic. And I just, just have a final note on the future work we are planning with the ensemble system. Of course, we will need to test for a summer heat case, let's say a heat wave, to bring out the benefits of dynamical coupling with SST, because that's where winds are lighter, so changing SST is likely to affect the boundary layer structure more. We should incorporate data assimilation in the model for comparison with the operational models, and also validate over, let's say, 2-3 years time, whatever the Met Office thinks is good for operational use. This is really the end of the presentation that I want to share with you today. I really hope it was interesting for you to listening, and I'm here to answer any question that you might have. Thank you very much.
Thanks a lot, Emanuele. If some of you want to ask a question to Emanuele, you can ask to him directly by raising your hand, and after I will give you the word. And to do it, I'll give you some instructions. It's a public chat box. If it doesn't work, or if I didn't see you quickly, please feel comfortable to write your question in the public chat box. Here we have a question. Bois, you can ask your question, please. Emanuele Bois, you can ask.
Sorry, I was muted. So, Emanuele Bois, I'm working at CNRM and LOPS 2. And first of all, thank you very much for this nice presentation. I really appreciated your work. It's very complete and very small. I have more like a comment than a question. mainly about the first part, the case study on your storms. I think that what you are seeing with the inclusion of the coupling with waves and the comparison of the different parameterization, namely the grade 1, grade 2, and then the coupling with wave, is more the result of a change of parameterization than a real coupling with wave. Because we did some work on the same topics, not in the on extratropical cyclone, but in med cyclones or storm surges. And the problem with the use of the Charnock parameter from the WaveWatch 3 system is that the variability due to the wave age is really low. So if you come back to the figure showing the comparison between the A-2 and the coupling with wave, you can see that the CD behavior with respect to U10 are very close to each other. Actually, there is a main difference, huge difference between that and hydraulic 1, for instance.
You mean this slide?
Yeah, exactly. You know, the green and the red clouds or clouds of dots are close to each other. And they are significantly different from the Edward one, for instance. And I think that what you are seeing, like the slowing down of the wind, or the surface wind, or the increase of the stress, is mainly due to this effect. And then you have a small variability from something in the red curve due probably to the wave age, but this variability is probably very slow, very small with respect to what you can have using another way of coupling with wave. And so I can send you some references on that, because we published some papers showing actually that the effect of a real coupling, taking into account real variability due to wave age, should be higher than that. So I can send that to you by email if you want.
Thank you so much. I think that's a very interesting point. I didn't mention this, but this is a really good point. I think what's interesting is that in the new draft parameterization, especially the bit from Coare 4.0, of course, there is an implicit dependence of the Charnock parameter on wave age, and that's why in slide, wait 1 second, is a bit before, yes. In slide 13, no, sorry, slide 12, I didn't mention alpha for A-2, because actually alpha in A-2 is not fixed, it depends on the winds. So A-2 also embeds a dependence on the Charnock parameter, just to add on your comment, which I think is very good. So yeah, if you have any reference, that would be most welcome. Thank you very much.
Welcome.
Florian, you had a question?
Yeah, I have several questions actually. So thanks a lot, Manuel, for your talk. It was very comprehensive, very interesting. So one point, maybe just to start related to Manuel's question. So you say that the ocean coupling does not have a strong impact, or weaker than the wave coupling. So is it technically possible to omit the ocean coupling and just have a wave coupling? Does it make sense?
Yeah, I think that's a good point. I think it's definitely there is the suite. How can I say, the operational model that also has wave coupling is there. So it's possible. The way why we structure the experiment like this, instead of having an atmosphere ocean and an atmosphere wave, is because when we have atmosphere ocean wave coupling, we also have an exchange between wave and ocean. So it was quite interesting for us also to feed that back in, because then we could see changes in the SST. But I think probably, as you say, that it would have been more clean if we'd also added an atmosphere wave coupling. I think it would have been more, can I say, rigorous or structured to also have an additional configuration with just atmosphere wave coupling.
Okay, thanks. So another question also related to the model setup. So you have a very, very complex now setup with high resolution atmosphere plus ocean plus waves and then an ensemble of it. So what is the added value of having convection permitting resolution in this? I mean, what would you expect if you would just run the ensemble model, the global model? I don't know the resolution it has from the UK Met Office with the other couplings.
I think that's a question I actually asked myself as well. I think it was, let's say, 1 year ago. So it's a very good question, I think. The very interesting part in here, I think, Florian, is that, of course, you know, I'm working with the Met Office, so I'll say that the technical, let's say, policy answer to you is that I have to use the model because it's useful for them. I mean, the very, let's say, political answer. The actually science answer is that the way that convection works, and I'm not an expert in convection, so please take what I'm saying with a pinch of salt, but how convection works, in my understanding, is that rather being always present in the Met Office models, it gets triggered by certain things. So, for example, by an accumulation of buoyancy in the surface and so on. So, at the beginning, what we thought we would have seen with a change in SST or a change in the boundary layer stability, we would have been triggering, let's say, more or less convection, depending to what we would have seen. And so, also the overall structure of the boundary layer would have changed significantly because the convection would have been triggered more or less. But the point here is that perhaps very interesting that the perturbations at the surface, at the interface between the air and the sea, are not really upscaling that much to the overall system. I didn't show it here, but the difference in pressure is about 2 hectopascal. I mean, of the system, the difference in the mean sea level pressure minimum is just 2 hectopascal. So what between the different couple configurations? So clearly, there is not really an impact that is propagating on the larger system. And we also looked at the vertical differences, but these differences are very localized to where the impact in coupling to ocean, coupling to wave is, and they're not being upscaled by convection or anything. And why is that? Actually, I don't know. This is, I think, why the perturbation waves are not really triggering convection, or more or less than it's already in the atmospheric model. I don't know, and that would be something I would really be keen on investigating further if I have time. I don't know if it answers it, Florian. Please iterate further if it's not satisfactory, let's say.
Yeah. No, thanks a lot. This also answers my next question that I don't need to ask anymore.
Okay.
I mean, you on one slide, I think it's 17, we see the where you show vertical profiles on temperature, if I'm correct, and wind. You actually see the differences above the boundary layer. So I was wondering how far. I mean,
yeah, that's the other interesting thing, I think. The problem is that most of these quantities, apart from wind speed, but for example, potential temperature, are not really model variables, are more like post-processed variables. So they tend to be out by schemes. And that's the same for boundary layer depth. It's not really a variable of the model. It's just something that is computed based on parameters. So it really depends on the surface layer scheme is being used. And yeah, as you say, like we see these differences, the profiles, but they're not really reflecting on the large scale, can I say that, or mesoscale at least, of the system. So somehow, yes, they are very confined to where the impact is in that sort of moment. So let's say this is 18 UTC, for example, Florian, right? So what you see, if you look at the vertical differences, what you see is that you have lots of differences in the structure of the atmosphere just around this point, and maybe at the position of the pressure minimum because it's close to it anyway. But that's about it. It's not propagating in the horizontal and in the vertical that much. And yeah, it really needs addressing, I think, at this point.
Okay, I would have a last small question.
Sure.
It just in the beginning, at some point you mentioned there is a stronger impact on winds than on gusts, and I don't really understand what you mean. Or maybe you can explain how do you define or what variable you use for wind and gust in this case.
I see. That's a very interesting point. Okay, let me just go here to slide 12. Yes. So this is the log law, right here. And in this log law, it's used by the model to compute the 10-meter wind speed. So the 10-meter wind speed is not something, it's not a model level. It's just output by the model at every time step. But at least it's based on variables that are part of the models, at least. So you have ideally you have, let's say, 70 vertical levels. So for example, you'd have the wind at 2.5 meter in height, at the 5 meter in height, at the 9 meter in height, whatever the levels are, I don't remember by heart. But you don't have a level at the meter. So you use the log law to interpolate the 10 meter wind speed. Interpolate, let's say, to calculate. But for the gusts, and I don't have the formula here actually, but what's really is that it's a contribution from the 10 meter wind speed, U10, and another factor that depends on the stability and the inherent turbulence of the boundary layer. Because the assumption that they made at the Met Office is that you have a signal, let's say, from the 10 meter wind, and then you have all the noise, from the turbulence. So they are saying the more turbulent is your boundary layer, the more gust, the more gassiness you'll see. But the problem that we are having here, and now I will go to slide, let's say, where I was talking about it, I think here is that, as you can see, Florian, the 10 meter wind speed are being decreased, and this is quite clear, and we know why. I think this figure is quite clear. But when we look at gust, for example, if you look at Z node, the increased roughness or momentum flux, that's enhanced. So the model thinks that there is more turbulence in the boundary. Actually, computes is set to have more turbulence in the boundary layer, which is exactly the reason why we're having the momentum flux in the first instance. So that's decreasing that distribution, the sort of gust speed coming from turbulence, proportional to the turbulence, is increased when I couple two waves or I change the drag parameterization. So overall, I don't really see a reduction in gas. I only see a partial reduction because that's partially offset by the enhanced gustiness due to the increase in the boundary layer characteristics caused in the first instance by coupling two waves or change drag parameterization. I don't know if that explains it, but yeah, that's my take on it.
Yeah, thanks a lot. Yeah, thanks a lot. So I stopped asking questions.
No worries.
Okay, does anyone else have a question to ask to Emanuele? Apparently no. So I think do you have something more to ask or to add, Emanuele?
No, just thank you very much for hosting me here. It was a pleasure for me to be here.
For me, it was a pleasure to organize and enjoy this with the others. I hope the others enjoy this seminar, and maybe it will be a pleasure to see you again in the seminar of LAERO, or maybe reading if you want to share. We are agree with that.
Yeah, definitely. Anyone more than welcome to come over. Well, not come over, but yeah, let's say virtually come over to Reading. Yeah, let's say if you have any question or or about the topic or so on, just please drop me an email also on ensemble work. I mean, yeah, whatever.
Yes, your email is on the LAERO website on the seminar webpage, so no trouble at all for that. If anyone wants to contact you, they can find your email there.
Mm-hmm.
So if anyone else want to add something, I think we can close this seminar. Thanks you a lot to watch it, and maybe it will be. I will enjoy to see you all on the other LAERO seminar.